Welcome and thank you for joining. In this lesson, we'll explore applications of higher order derivatives. Our focus will be on the position function. Remember that position function, which is indicated by letter S, T, at least in calculus, indicates the location of a point from the point of reference or the starting point. Now, position is a vector quantity. That's not what we're discussing in here, but I'm just mentioning this to indicate that position will tell us not just what the distance of an object is from the initial point, but also the exact location of it. Now, how fast the position is changing will tell us what the rate of change of position is changing, or in other words, more commonly in everyday life, we call it the speed of the function. Now, because position is a vector quantity that tells us the location of a point, not just the magnitude of it, so not just the distance, then we'll say that the rate of change of position will give what we call the velocity of a function, which in itself is also a vector quantity. So it tells us not only the magnitude, but also the direction of the motion. Now, velocity is equal to the first derivative of position, or in Leibniz notation, we write ds dt. Now, velocity in itself can change as well. So when we drive, for example, we don't always drive at a very, like a constant speed, a very constant speed. So velocity changes over time. And the rate of change of velocity is measured by its acceleration. So acceleration is the rate of change of velocity, or since velocity is derivative of position, is the second derivative of position. So we're going to say that acceleration is the first derivative of velocity or the second derivative of position. Now, in order to best understand the meaning of position, velocity, acceleration, and how they are connected in calculus, I think it's best that we look into this beautiful graph, which is excerpted by the calculus textbook, and analyze the motion in the different intervals as indicated. So we have the graph that represents the relationship between position and time. At the origin, and that's what we normally do, the origin is the initial point or the point of reference. And we have divided the graph into 1, 2, 3, 4, 5, 6 different intervals, and we'll describe the motion of the object in the 6 different intervals. And when we say the motion, we'll describe the position, velocity, and acceleration. So we're going to start off with the motion from A to B. So as you can see, A to B is a horizontal line. So for the first 2 meters or 2 seconds, we're not given the units here, it doesn't really matter. We see that the position hasn't changed. So if the position doesn't change, it means that the object is not moving. In other words, we say that the object is stationary. So a non-moving object means that a non-changing position. So the rate of change of position will be equal to 0, or velocity is 0. And when the velocity is equal to 0, it means that the rate of change of velocity in the interval, because velocity is 0 at every point in the interval, would be 0, which means that makes the acceleration equal to 0. Again, velocity is not changing over the entire interval. So we're going to move on to point from B to C. So again, as you can see here, the object is moving now away from the initial point because the position was 0 at B and it became about 2 units at point C. So the position is increasing over time. So in this case, we're going to say that the object is moving away from the initial point. Now let's talk velocity. Velocity is the rate of change of position. So if you drew the tangent lines anywhere on the graph of the position on the interval BC, you see that the tangents will have positive slopes. Positive slope, positive derivative, and positive derivative of position means positive velocity. So we'll say that velocity is positive because the position is increasing or going up. Now, let's take a look at the trend in the values of velocity. So velocity was quite low in here, and it became more positive and even more positive as it moved towards C. So that tells us that the velocity itself is increasing. So the rate of change of velocity, it's an increasing rate. So that must be positive. So we'll say that the acceleration is positive, and that is because velocity is increasing. I hope that you got the hang of it, because the reasoning for the rest of the intervals is quite similar. So from C to D, the object is still moving away from the initial point or point of reference. We know this because at C we were at 2 units and then it goes at 3 units. So we're going to say that from C to D, the object is moving away from the initial point. Let's talk velocity. Velocity is positive, but still positive, and right here it will hit 0. So we're going to say from C to D, velocity is positive because position is increasing. Now, when you look at the slope of the tangent or velocity as we go left to right, remember we always read graphs just like we read books in English, left to right. Velocity is positive, but it's getting smaller and preparing to become 0 at D. So that tells us that the rate of change of velocity is negative, or in other words, acceleration is negative because velocity is decreasing in value. Now, exactly at point D, you see that the velocity will be equal to 0. So that means that the object is not moving, but because this is part of a continuous motion, so it's not an interval, it's just a point, then we're going to say that the object has temporarily stopped at a fraction of a second. And at that very moment, just at that very moment, velocity will be equal to 0. Now, when you think about acceleration measures the rate of change. So the acceleration or the rate of change of velocity is going from positive, less positive, 0, negative. So the trend in the rate of change of velocity or acceleration is consistent and continuous in here. So we're going to say that the acceleration in this case will be still negative at point D because velocity is still on the decrease and is just passing through its 0, and any quantity to go from positive to negative, it has to pass through its 0. And this is probably the more, confusing point on this graph. But again, I'm going to explain it one more time. So velocity in itself, yes, does become 0, but the acceleration never stopped changing or following the same trend. So the acceleration goes from positive to 0 to negative. So the trend throughout this part would be negative. So the velocity is decreasing continuously here, and that means that the acceleration will be negative, including point D. Now, from point D to point E, as you can see, the object is getting closer to the initial point. So it was at 3 units far and now at 2.5 units far. So therefore, we're going to say that the object is moving towards or closer to the initial point. When you look at velocity, which is basically the slope of the tangent, you can tell that the slope of the tangent is negative. So that means that velocity is negative. Now, bear in mind that doesn't mean that the object is moving faster or slower. It's just the direction that is in the negatives now. So for example, right here, velocity is positive, but that doesn't mean that just because velocity is negative, the object is going slower. It is going faster. It's negative only because it's going towards the initial point, not because it's smaller. Okay, so it's probably faster at this point close to E here than at this point close to D on the left side of it. The speed itself then. Now, we're going to say that velocity is negative because position is decreasing. Now, let's talk acceleration. So velocity is negative, but it continues to become more and more negative as we get closer to point E. So in this case, then we're going to say that the acceleration must be negative. And that is because velocity is on the decrease in here. So going from 0 to more negative. Now from point E to point F, So we have a smoother curve in here. As you can see, the object is still getting closer to the initial point, and that's because the distance from 2.5 becomes 2 units here. So we're going to say that the object is moving towards the initial point. When it comes to velocity, all we have to do is look at the slope of the tangent, still negative, getting 0, close to f is exactly 0. And we'll say that in this case, velocity is negative because position is negative, so it's going towards the initial point. Now, from point F to point G, as you can see that, let's finish this up. So even though the velocity is negative, it's increasing in value because it goes from negative to close to 0, which means that the quantity that represents velocity would be from negative to 0. It's an increasing quantity, which means that the acceleration would be positive because velocity is increasing. So last we have the time interval from F to G. That is very similar from F to B. As you can see here, position is not changing. So the object is away from the initial point, so it's not at the initial point, but it's not moving, so it's taken the object, or the person who is driving or riding the object is, the vehicle is taking a break in here. So we're going to say that the object at this point, at this interval, from F to G is not moving, is stationary, which makes the rate of change of position 0, and acceleration as a result will be also 0 because velocity is not changing. So I hope this made sense, and I hope that this kind of shed some light on understanding how position, velocity, and acceleration are connected to each other, and it helped you visualize how the motion of an object can happen, how the negative values, to interpret negative and positive values of velocity and acceleration. And in the next part of this lesson, we'll look into the algebraic representation of the velocity, position, and acceleration. Bye for now and have a beautiful day.